In section 5.8, we discuss the average value of a function, and there are basically two approaches we'll look at that you've seen over the years for finding an average value. And they've used the same word for both of them, but really, if you look at them, you might wonder why they're both averages, whether they really amount to the same thing. The first one is if we look at this, if we, one computational approach is to compute averages we would for a list of numbers. If you had a list of 5 numbers and you wanted to compute their average, you'd add the 5 numbers up and divide by 5. This leads to some problems when we're dealing with functions, because over an interval, a function will have an infinite number of values, which would be tough to add them up, and then how do you divide by that infinity when you get done? So we have that idea, then we'll look at how we can approach that. Then there's a second approach. There's the approach where you calculate the average speed, or maybe I should say the average velocity. And to calculate the average velocity, you take the change in position divided by the change in time. And those, are two different approaches to finding an average. What we'll see here is that those two approaches lead to the same result, and basically we can use those to calculate things. We're going to need a little background before we can discuss this, and that is, let's see if I can move this down a little bit. That is, we need to remember the definition of the definite integral. The definite integral is the limit, as the maximum of delta x approaches 0 of the sum as k goes from 1 to n of f of x sub k star times delta x sub k. And when it exists, of course, we use this notation. It's the definite integral. And then we saw with the fundamental theorem of calculus is if f is continuous on the interval, then we can take an antiderivative and evaluate it at the upper limit, evaluate it at the lower limit, and subtract and get and evaluate that limit easily, all right, without too much ado. All right, so let's start to think about this. Let's suppose that we wanted to calculate the average value of a function. Well, we might start by estimating it. If we wanted to calculate the average age of a person living in the United States, we wouldn't try to contact everyone, because in the course of doing so, we wouldn't be able to. Some people would be born, and some people would die, and such. So we couldn't really compute that. But what we would do is we would take a sample. So let's suppose we did that with a function. We take a sample. Let's suppose we pick 3 different values, one at x sub 1 star, one at x sub 2 star, one at x sub 3 star, added them up and divided by 3. This would give us an estimate of an average value. And of course, we could write this in summation notation as 1/3 the sum as k goes from 1 to 3 of x sub k star. And let's see, what we might do then is we might, this is the function x squared plus 5, and if I look at it, I see that I've chosen 3 values, and the average I got was about 12.96. What we might do at that point is we might increase the number of values, and I can't increase them forever, but I can keep on increasing it until I have I have 20 values, I believe, here in the code is, and this gives me, an average of about 15.47. Let's keep that in mind, because we'll actually compute the average value of this in a little bit. And so what we might do is we might think of the average value in this way, but then let the number of values that we're using go to infinity. So we'll use n values. So we have the sum as k goes from 1 to n of x sub k star, and then divided by n, and let n go to infinity. And that would give us the average value. That seems to make sense. It seems to be reasonable. All right, well, how do we actually compute that average? Okay, well, let's see. What we can say is this. I want to compare a couple of things here. All right, and notice that this limit that we're going to use to compute the average value, we're going to sum up function values and divide by the number of them, and let the number of them go to infinity. All right, if I do that, all right, I want to compare that with the definite integral, and there's some differences. If I look at this, there are a couple of differences that I have to keep in mind here. All right. First off, notice that in the definite integral, I have this delta x sub k factor, which I don't have in the summation that I use to calculate average. So this delta x sub k is in the definite integral, not in the average computation. Okay? The second thing is that I have this 1 over n in the average computation, but not in the definite integral. So we have the 1 over n in the average, but not in the integral. And finally, there's one more thing, is that if I look at the limits, here is the limit as n goes to infinity, and this is the limit as the maximum of delta x sub k's goes to 0. And so what about that we had in the average? The limit as n approaches infinity in the definite integral we have the limit as the maximum of the delta x sub k's goes to 0. So how do we rectify these two things? And we want to, so that we can use the definite integral to calculate the average value. All right, so the first thing is, let's take a look at this delta x sub k issue. Now notice in the definite integral we have the subscript k because the delta x's can be all different sizes. All right, but that's not so good when we're calculating an average. Let me illustrate. Here is that estimate this function again is x squared plus 5. And the thing is, if we let the delta x's, if we let the size of these intervals, all right, be different, all right, we could have things like this happen. We might have a place where we make the delta x's big at the beginning and small as we go on, and then we'd have sampled a larger number of values. All right, it's a large number of values from the sampling one from each subdivision, a larger number of values where the function is big. Or we could have just the reverse effect, and this would give us an average value that would give us a value that would appear too large. That would be too large. All right, or they could be skewed the other way, where we're picking a lot of delta x's are small at the beginning and large at the end, and then we'd have a small estimate for our average value be too small. All right, so what can we do to make sure that the values that we sample are evenly spaced throughout the interval? Well, the thing is, what we can do is we can make sure that all of the delta x's are the same size. So what I have is, if I have n intervals, I'll have b minus a over n, which we had called delta x back in section 5.4, and let all the delta x sub k's be that same value. So delta x sub 1 is that same value, delta x sub 2 is that same value. And then as we choose a point from each of those intervals, we'd have them all be the same size. So now let's take a look at this, at how we would calculate this average value. All right, what I can do is I can rewrite this as the limit as n goes to infinity. This was that limit that we used that would give us our average value of 1 over n, all right, times the sum as k goes from 1 to n of f of x sub k star times, all right, now watch carefully, times delta x sub k over delta x. And the thing is, why do I have this here? Remember, they're all the same size. So we called all these delta x sub k's, we called it delta x. And this delta x is constant then. So we could take that out. So this would be equal to the limit as n goes to infinity. All right, and maybe I should put a little note up here that all the delta x sub k's are equal to delta x for every k. And remember, that made sure that we were spacing out evenly the sample points where we were calculating the x sub k stars. All right, then we could take this out, and what we'd have is 1 over n. This is constant in all the terms, so I can take it out of the summation of the sum as k goes from 1 to infinity, to n, sorry, of f of x sub k star times delta x sub k. And now this sum looks precisely like the sum that we have in a definite integral. All right, we have a little work to do out in front. Recall that delta x was the length of the interval, b minus a, divided by the number of some. So 1 over delta x will be the reciprocal of this. So this would be the limit as n goes to infinity of 1 over n times n over b minus a times the sum as k goes from 1 to n of f of x sub k star times delta x sub k. All right, and of course here the n's cancel. B minus a is a constant, it's the length of the interval, so I can take that out of, it doesn't change with n, so I can take that out of the limit, and I'd have 1 over b minus a times the limit as n goes to infinity of the sum as k goes from 1 to n of f of x sub k star times delta x sub k. And now remember that each of the delta x sub k's, all right, was delta x, all right, which was b minus a over n. So as n goes to infinity, all the delta x sub k's go to 0. They're all the same size, so the biggest one of them goes to 0. So this would be the same thing as 1 over b minus a times the limit as the maximum of the delta x sub k's goes to 0 of this sum as k goes from 1 to n of f of x sub k star times delta x sub k. And this is exactly the definite integral, so this would be 1 over b minus a times the integral from a to b of f of x dx. So we have then that the average value is precisely the reciprocal of the interval length, okay, 1 over the length of the integral, 1 over the length of the interval, times the integral from a to b of f of x dx. All right, let's take a look at an example of that. All right, let's actually calculate the average value of x squared plus 5 on the interval from 1 to 5. So the average value, remember when we did this before and we got the 20 values, it was about 15.47 was an estimate. So the average now, using that formula, is going to be 1 over the length of the integral, that would be 5 minus 1, times the integral from 1 to 5 of x squared plus 5 dx. And this is going to be 1/4. All right, let's see, when I anti-differentiate this, I'll get x to the third over 3 plus 5x, and I'll have to evaluate that from 1 to 5. This will be 1/4. All right, and then times, let's see, when I evaluate this at 5, I'll get 125 over 3. 5 cubed is 125. All right, plus 25 minus the value at 1. The value at 1 is going to be 1 over 3. 1 cubed is 1 plus 5. And I have to multiply all that times 1/3. So notice, let's see, what will we have here? We'll have 1/4 times, let's see, 125 and over 3 minus 1/3 is 124 over 3. All right, plus 25 minus 5 is 20. And so what I'll have then is multiplying through by 1/4. Well, 4 goes into 124. 4 goes into 124 31 times. So that'll be 31/3 plus 5. And 5 is 15/3. So this would be 45, 31/3 plus 15/3. That would be 46/3, which is 15 1/3, or 15.3. And notice, so our estimate of 15.47 was not too far off. It was actually a pretty good estimate. Let's take a look at one other thing I'd like to show you, is the geometry of the average value. All right, now remember, this average value is the the reciprocal of the interval length, all right, 5 minus 1 in this case, right, times times the definite integral. If we have a positive function, that would be the area under the curve. So if I multiply both sides by the length of the interval, b minus a, then this value, b minus a times the average value, will be the area under the curve. If I would think about this as the width, all right, as the width and the height of a rectangle, all right, this average value is going to be the height of a rectangle with the width, that's going to be the length of the interval, and that area of that rectangle is going to have to be precisely the area under the curve, precisely the definite integral. All right, this one looks too small because look at how all the area I'm leaving out and only the area that I have in. Let's take a look at an example of that. Okay, if I look at this function, and what I'm going to do is I'm going to adjust the height of this rectangle, and I'm going to adjust the height of this rectangle, and the program will highlight it when it gets to the average value. So right there, we're at the average value. This rectangle covering the same interval, all right, it has a height, the average value is its height, and the area of that rectangle is precisely the area under the curve. The area of the pink rectangle is precisely the blue area that's underneath the curve. And that's what the average value calculates, okay? All right, next we'll look at some examples or some applications of average value. We'll do that in the next videos.